Thank you very much for this very kind introduction. I'm truly honored and privileged to be giving this memorial lecture in the name of a legendary figure, Shri J.R.D. Tata. I gave this talk, J.R.D. Tata Memorial Lecture, probably in the same hall, around the same time, 6 years back. So when I got a letter from Professor Vaya on January 15th this year, he wrote very clearly, we remember you gave a talk, but you were wearing different hat. So with this new hat which you have, we would like to hear you. So without thinking much, I said, since it has come from TIFR, and you know TIFR, when something comes, you can't refuse. It's one of the most prestigious place with high intellectual atmosphere, very, very intelligent people. So I said, we will worry about what to talk, but I accepted. That was in January. And till May, I kept on getting reminders from Professor Vaya to give us a title of the talk. And that was my problem, because I had not made up my mind what to talk on. So I had given a very general title, Perspective on Science for Sustainable Future. That will cut across many areas, I thought, and I gave that title just to really stop getting the emails from Professor Vaya about the title. Then a week or 10 days back, when I started preparing, it dawned on me that this is not something I can engage the intellectuals of the world for 45 to 50 minutes. I can talk for maybe 15 minutes on that, but not really for 50 minutes without really testing your patience. So I concocted this title on almost without thinking too much, a personal scientific journey covering best of both worlds, from Vigyan to Vigyan Bhawan. Trust me, I had not really thought about what I'll talk, but I was very clear that I don't want to miss out on telling you something which is very exciting to us in the domain of science, and take you to something which I do for 90% of my time now, and 10% to 15%, I'm still plugged into science because I still have my graduate students in IISc Bangalore. So that is the genesis of this title. And the reason I'm here is because this invitation from TIFR is so very special and prestigious. So I thought I'll share both the sides. Now this painting which you see here, I'll show you a few of these paintings generated AI tool, which we just generated 2 days back, which you can use ChatGPT 4, or you can do, this is done with Dreamscape. So I just gave a keyword, journey of a scientist from science to policy. So now you can use your imagination to see what it has created. But there are many things, so I was amused. So I thought I'll show this, because in the evening, you cannot be giving a very serious talk. So I thought I'll amuse you on the way with some of these things. So I thought, instead of talking one specific thing, it gave me an opportunity to also see how my interests have evolved over a period of time. And I really, it is just a personal recollection, and it is not meant for any values or value judgments and so on. So this is a very personal journey, which I started in 1972 when I joined BARC training school in Bombay, as was mentioned. And in 1974, I opted in 73, I opted after completing the training school to move to material science lab in what was called Reactor Research Center at that time, and which was headed by, as was mentioned, Dr. G. Venkatraman, who was building up this group in Kalpakkam. And when I reached there in June 2020, in 1974, I was told to build an optics laboratory on materials. That was the mandate. That's it. And I was 22-year-old at that time. And I had no previous experience of building up a research group because I myself didn't have enough experience. So we started thinking what to do. So the order came, you build Raman spectroscopy lab, but without importing anything. Dr. G. Venkatraman, as you know, all of you know him more than me, some of you, he was truly a nationalist and he didn't want to depend on imported equipments. So reluctantly he agreed to buy a double grating monochromator. And he says, that's it. So around that monochromator, we built up the Raman lab. So I had to build along with my two young colleagues who joined me a year and 2 years later, Akhilesh and Uma. We started building helium neon and helium cadmium lasers of about 30 milliwatt, and it was 1.5 meter long. And with the gas filling system, which was occupying the whole wall, with about 20 stopcocks, which were leaky and so on. So it was a struggle, but in the end, after 2 years, 1.5 years of struggle, we built those lasers, we assembled Raman spectrometer, made cryostats and furnaces and electronics, a single photon counting with the electronics group, and we recorded our first spectrum around 1978 or 79, 78. So it took us 5 to 6 years, 5 years almost, to come to that stage. But we were not worried because in DIE, nobody asks you if your boss is happy. That's the good point. And we thrived in that. But along in that 5, 6 years, we really devoted ourselves to learn physics because some young people had joined and trained people, very professional people like Professor V. Balakrishnan from TIFR, Sushanta Datta Gupta, Dr. Sahu, and all have joined. So we learned some science physics from them. And we measured the Raman experiments. And this is the very early experiment, 42 years back, we published on potash alum, which is potassium aluminium sulfate, and look at Raman spectrum. And these two lines are the vibrational mode of a sulfate ion because the sulfate ions are in two inequivalent crystallographic orientation. And the area ratio between them as a function of temperature did not follow Arrhenius law. That was thankful. Because if it was Arrhenius, it would have been boring physics. Because it was non-trivial, we collaborated with Professor Datta Gupta, who was expert in stochastic relaxation dynamics. And we also learned all the Feynman diagrams because anharmonic contributions had to be added. And we did publish it. And the lesson which we learned at that time, that designing and fabricating instruments is an integral part of research journey. You can't separate it. And data provided us opportunity to learn new theoretical tools like stochastic theory of line shape, continuous time random walk, and phonon anharmonic interactions. So that led to my thesis in 1982, 10 years after my master's, named Rotational and Vibrational Relaxation, Stochastic Theory of Line Shape and Continuous Time Random Walk. So this thesis is 40% experiments and 60% theory. So that also taught us an important lesson that there is no divide, which is a very artificial in my mind, between theory and experiment. And the theorists should be able to appreciate experiment, and experimentalists should know enough theory to look to ask the right questions. So that was lucky. But soon we realized after this was in 1982 that the laser power, which was only 20 to 30 milliwatt, was not enough for Raman scattering. We needed much more power and we were limited. So just that constraint, that we could not import any argon ion laser, that was prohibited. We started looking at alternate physics which could be done with these lasers, and that led us to soft condensed matter, where we measured the structure factor S of Q, where Q is the wave vector transfer, and dynamic light scattering from the intensity correlation from colloidal crystals and colloidal suspensions. So this was a lucky break which came out of constraints which were there because we did not have high power lasers. And 83 to 85, I had a very, very fortunate lucky break to have postdocs with Professor Cardona in Max Planck Institute, where we worked on variety of things, and including semiconductor superlattices, which were just getting being studied at that time. These are alternate layers of two semiconductors. Each layer is only about 20 angstrom. So this is the nanoscience in the very beginning, but it was not called nanoscience at that time. And that gave rise to very interesting physics, which I just give you an example. So when you have particle in a box, this is the quantum mechanics 101. If they are confined in a box, you have the quantization of the energy levels and the wave functions, 1, 2, 3, they have different parities, odd and even parity. Question was, can you ask the same question for phonons instead of electrons? That was the question, which was not known at that time. We asked that question and we did Raman experiment and showed that instead of a very sharp line from gallium arsenide, which was the material of the superlattice with aluminium arsenide, we got large number of Raman modes depending on what symmetry we do. So we could separate odd and even parity, and we could map the phonon dispersion curve with Raman scattering, which is usually a zero wave vector technique. And this was something which was very exciting, that was published in 1985. And back to back, which has never happened, I understand, in PRL, we had submitted 2 papers, 4-page each. And the second paper was on the interface phonon, which only exists at the boundary between the 2 semiconductors. And this was called interface phonons. And of course, then we had large number of citations and so on. And then this field has thrived from that time onward. So let me do a quick fast forward. After coming back to Kalpakkam in June of 1985, we realized that Raman scattering cannot be done in Kalpakkam at the level which is happening internationally. So we focused more on soft matter, which has been most rewarding. And in 1988, when I moved to Bangalore, ISC Bangalore physics department, I was given 2 empty labs. There was no instruments, and this was a contrast from a very good lab in Kalpakkam. I decided to move, and some people also called it a suicide mission, which luckily I didn't listen to. And we set up the lab, and then from there we had Raman lab, also added high pressure because of Professor A. Jayaraman, who spent a sabbatical in physics department. And then started Brilliant scattering, which is not written here in JNC, started ultra-fast spectroscopy, time-resolved femtosecond spectroscopy in the next few years, and more recently, time-resolved second harmonic generation, terahertz. All that is just so wonderful to learn new subject every 5 years and do nice experiments. This is the gift of gratitude of doing science in this country, because you can afford to do all this if the funding agencies are convinced. And here I should place on record, which I have done earlier also, my special thanks to Dr. Chidambaram, because after I shifted to ISC you are given actually few rupees per year. At that time, it was 10,000 rupees, of course, not few, as a startup grant. I got much more grant because I said without that we can't start, but it was not enough to start a full lab. So I wrote to DST for a project on Raman spectroscopy. And Dr. Chidambaram, I don't know if you remember, you were the RAC chairperson, and we had a discussion in the guest house that why can't you build the Raman spectrometer in IISc? Same question. Then I had to explain that if that happens, then again we will be nowhere. So please allow me to buy a Raman spectrometer and a argon ion laser, and remaining things I'll build. So luckily he had faith in me, and DST gave me grants to build up the lab. So it has been a nice struggle. Along the way, we have learned a lot. And in and lipids, that also brought me closer to some aspects of biophysics. System, and this is a whole field which is totally open from the physics point of view. So we discovered in this surfactant systems that the viscosity depends very strongly on the shear rate, that too in a very, very well-defined time manner, which goes from a nice periodicity to a chaotic behavior. So the entire physics of chaotic dynamics we could study experimentally in the sheared soft matter. And more recently, I'll cut the story short, more recently the interest shifted to active matter, and this is what I talked 6 years back in this very hall, where we looked at flocking behavior in this active matter. And more recently in stochastic thermodynamics, I'll take few minutes to tell you what is so exciting about this, which made me give you the title from Vigyan to Vigyan Bhawan. So the next 15 minutes, I'll tell you something we feel very excited. We think it's a something nice, it can be built upon. And I'll just share with you in a language which is not too technical. So I have to keep track on time. So I don't know, when did I start? 4:45? 4:45. Okay. So this is just, one example which I wanted to give on this time Raman spectroscopy, where we looked at, nano devices in situ mode. So this was the graphene field effect transistor. When the device is working, we see what are the changes in Raman signals. So that Raman became the eyes and ears of the nano device in situ. And that gave us deep insight into the mechanisms which control the mobility of the carriers in nano devices. So there is an interesting anecdote here. This paper so that time we were not making these devices. These devices came from Andre Gein's group, who later got the Nobel Prize. At that time, we submitted this paper to physical review letters. So it will be comforting for you to know that this paper was rejected. It did not go to refereeing. It said, the editor said, oh, somebody has done on something. You have done yourself a transistor in carbon nanotube. What is so new? We said, thank you very much. We submitted the same paper with some changes to Nature Nanotechnology, which was hugely difficult, we thought, but we thought we should take a chance. And luckily, it went through without much trouble. And good news is that now the data we generated on looking at Raman signatures as a function of N and P doping has now become a metrology tool. And right now it has about more than 4,000 citations, because this is a non-destructive measurement of doping in a working device. So what it led to, that led us that we must make this nano devices in IISc. Believe me, it was a struggle. We wrote the projects, we went to the director, and said that we must have a clean room facility. We should have the fabrication where we can make this nano devices with e-beam lithography. Fortunately, things were put together and we converted, the group converted scanning electron microscope to e-beam lithography, and all our further experiments were done with ISC made devices on graphene, MOS2 and so on. So this is what I wanted to show, that how it led to the entire new development of this nano devices fabrication in my group and many other groups in ISC. So let me now come to in next 10 minutes, next 15 minutes, what I want to tell you about stochastic thermodynamics. So I have to take one step back and remind you of your high school physics, that we know that heat engines, our life revolves around that. The modern life cannot be without the use of heat engines. And this converts heat or chemical energy into mechanical work. That is the general principle. And this is a wonderful milestone in the foundation of classical thermodynamics, which was known. The application of that came by Carnot in 1824 for this device, for this heat engine. So what do you have? You have the first law of thermodynamics. You know first law of thermodynamics. You can get the efficiency out. You can know the Carnot efficiency, which is all very well known to you. You combine first and second law of thermodynamics and you look at the heat engine, entropy and so on. So what do you have in heat engine? You have a hot source, you have a cold source, you have the gas. So these are the two engines which are called Carnot engine and Stirling engine. I'll just discuss the Stirling engine in a little bit in 2 minutes, because that's what we'll be using in our next discussion. So what do you have in a Stirling engine? Stirling engine, you have a gas at a high temperature. So the gas is in touch with the heat exchangers. It expands. So that's where you get the useful work out. This is the isothermal expansion. So the system, the engine and the heat exchangers are kept at high temperature by the input of energy. It could be from any source. And that is where you get the useful work done if you are just doing correctly. At this stage, you do a isochoric cooling, which means you now, so the heat has been absorbed from the reservoir and gas has expanded. You have done some useful work, but you have to have a cyclic way, because one cycle is not enough. So you do at the same volume, you just make sure that the gas is cold, connected to the cold reservoir. At this time, you do the compression where you work on the system. And at this stage, you get isochoric heating. And so the work is, useful work is done here. And if this work is much more than this, you will get the useful work out. That is the principle of Stirling engine, similar to Carnot, but the efficiencies is less than Carnot, which is what I have written here, work done and efficiency. And this is something very well known in the last 250 years. And this has been, there are beautiful toy models also available in the market. But what you have to know for the last 250 years, that whatever we have discussed is in the reversible limit, which means you do very, very slow work. So everything is extremely slow, so that you always have equilibrium between reservoir and the engine, because otherwise then only you get the complete work done. So this is called the cycle time, how much it takes this, and that gives you the maximum work done at a large tau, which is written work done. So you would like to have very, very slow engine so that you get a lot of work done, and efficiency is also maximum. As you make the engine faster, means small cycle time, you have a problem with demand and supply. It cannot do at such a rate, and the work done will decrease. And at some time, it will not be an engine, it will be a refrigerator, because it will not respond. and efficiency will also become less than zero. So what happens is you would like to be in this sweet spot, but the trouble is life is not so simple. At that time, if you look at what is the useful power, because you need power, that's why you are making an engine. You have to do what is the power you can drive from this engine? The power will be exactly zero asymptotically, because power is work done divided by the cycle time. And for large tau, the power is extremely small. At smaller tau, power is extremely small because it has already not responding. So there is an optimum value of the cycle time where the power is maximum, but efficiency is not, efficiency you have to live with it. This is called Curzon-Elbaum efficiency. This is true for all engines made so far. All the engines, whether it is a nuclear reactor, thermal reactor, everything is some variation of that. And you live with Curzon-Elbaum efficiency and not the Carnot efficiency. Carnot efficiency is much more than this. So this is a paradigm. It's called power efficiency trade-off in macroscopic engines. So you have to sacrifice something to get out. So what have you sacrificed? You have sacrificed efficiency to get the maximum power, which is what you want to utilize for your use. So at fast cycle time, as I told you, you bring irreversibility into engine performance. I want you to keep that in mind. I'll come back on how we started. So now the goal in the entire community is to miniaturize the engines. Why do you want to miniaturize? At nanoscale, if you can make it, can you do transport cargo inside cell? Of course, very, very fascinating science fiction question right now. And can you really basically understand this field? Why do you need to do that? The reason is when you have nano means very, very few particles of gas, very, very few, not 10 to the power 23 per unit volume, but very few in a nano system. Engine is in nano size. Your performance will depend strongly on the environment because the energies are somewhat similar. And the fluctuations, when you have very small particles, the huge fluctuation, you will not really work with the average quantities. Average is same as the variance. This is the problem of small system. So it is not a mechanical miniaturization which is a challenge. The challenge is you have to work with fluctuating thermodynamic quantities. That fluctuations, how do you get heat and work calculate is the whole paradigm of stochastic thermodynamics. It is thermodynamics with fluctuating quantities. And the heat to work in fluctuation dominated regime is the new fever in this field to see how do you make such stochastic thermodynamics work for you? How do you make practical systems? And that practical system was demonstrated a few years back in 2012 by a German group with a very, very clever technique. So what they did, piston and a cylinder were replaced by an optical tweezer which confined only one colloidal particle. Please remember, it's in water, colloids are moving, you trap a colloidal particle. That trap acts like a piston and a cylinder. So by changing the stiffness of the potential, you can make you can expand or control in a very, very precise manner. So the piston moving out is reducing the laser power and so on. So the beauty is you can now make an engine with one colloidal particle and not 10 raised to the power 23. That is the achievement of this paper. So the colloidal particles are in water. So when you change the water temperature, let's say from 70 degrees centigrade to room temperature, these are the T hot and T cold, you get the work done. And they demonstrated that whatever you get, so what you measure is the particle displacement in time and you get the probability distribution. That's all you have. From probability distribution of P of X, now there is a stochastic thermodynamics framework which has been done. This is just a setup optical tweezer. It's a very straightforward. I'm sure in TIFR many groups are using, which is a wonderful tool in biological science. You focus the laser in a microscope, and this is where you trap a colloidal particle, and you can move around like a tweezer. So I will not go over the equations, but once you know the probability distribution, you can really get all the heat and work done. And what it was found in 2012, that when you operate between the thermal baths at 70 degree or 80 degrees centigrade and room temperature, whatever you measure, the work done, efficiency and power, they exactly match what you calculate for macroscopic engines. So the microscopic engine gives you the macroscopic thing when you work with this thermal reservoirs. At that time, we came into picture, and we were thinking of stochastic thermodynamics from other problems. And we said, what happens if the bath themselves are out of equilibrium? It's not a thermal bath, it's a non-equilibrium reservoir. There is no macroscopic equivalent. There is nothing like environment which you can play with and you can say that I'll make it thermal or non-thermal. And this is where we wanted to see. Now in these engines, please keep one thing in mind. These are not the ones which I will run tomorrow and give you the useful work and run something in my body. It is still far from that. But it opens up a huge paradigm. This is the beginning of the game, which establishes fundamental principles that govern the motion of motors, biological motors at microscale. So this is where the understanding has to be evolved, and non-equilibrium reservoir this is where the biology also works. How do we do that? This is what we did in 2016. In this work, we vary. So in addition to the colloidal particle, we also put bacteria into it. And the temperature of that whole bath by another channel, we varied between simply 313 Kelvin, little bit feverish, and 290 Kelvin. At 313, bacteria are very, very agitated. Very agitated. They really move around. Bacteria is not trapped. Trapping is still one single colloidal particle. But at 290, they do not die, but they are very sluggish. So these bacteria, I will not give you detail. This is something I touched upon in my last talk here, which was the beginning of these experiments. And what we showed was that indeed that probability distribution very enormously changes when you do, instead of now isothermal, we are doing isoactivity. High activity, it is like a high effective temperature. Then you have cooling of water, which means bacteria cool down. At low activity, then again heating and this thing. This, if the bacteria was not there, the engine will give you very, very small work, which I'll show you, and small efficiency. But using this bacterial activity to get in high effective temperature, how do we define it? Because you have to define some bacterial activity. Probability distribution is highly non-Gaussian. Using this variance, the width of this, we can simply equate to kBT. This T is not the temperature of the reservoir. It is the effective temperature seen by the colloidal particle, because bacteria are putting all this noise, and that noise is getting converted into this heat. And this is what we did at that time. And we showed that the thermal, without the bacteria, this was the cumulative work done, very, very small on this scale, expanded here, -3 in this unit. But when we put this bacteria between this low and high activity, you can see that it increases 250 times. So we can now use the bacterial activity to make it a non-equilibrium reservoir. And we showed that indeed you can do many, many T activity, various activities of bacteria. And we showed at that time that the work done, the useful work done, which is negative by convention, without bacteria, it's very, very small, 0.03. And that becomes huge as you increase the activity temperature difference. And this is something which has not been shown and we show it can be done with non-equilibrium reservoir. And the efficiency, which is here without bacteria, it jumps, and you can see that it even crosses the theoretical limit for this system, which is what is known the Stirling efficiency, which is what is given here. It even exceeds that. It should not be surprising because we are in a non-equilibrium system. So there is no reason to believe that the equilibrium physics prediction will go through. This is something I thought I'll tell you. And this is the work which we did in collaboration with our biology colleagues, which I mentioned, Professor Dipankar Chatterjee and his student who gave us the right kind of bacteria, and the graduate student, Sudhish. This is the work in his thesis, which he submitted 2019, and it has still taken us another year and a half to do the last part, which I'll tell you in next few minutes. So it's, and my long-term collaborator, very, very active collaboration with Professor Rajesh Ganpati, who is in JNC, and his student Nilendu Rai. So it has been truly a collaborative work, wonderful experience, because these experiments, please trust me, extraordinarily difficult. Because you have to trap a particle and do this cycling without any artifact. So it takes enormous amount of patience and work, and hats off to Sudhish and more recently Nilendu in JNC, who are able to perform these experiments. So this is the paper I discussed, and more recently we have done two engines coupled. What happens then? If you have two coupled engines in equilibrium, nothing will happen. It will be just additive. But now when you have two non-equilibrium systems, you can really do synergy. And what we showed, that you can do synergistic action in coupled engines due to some non-conservative flows. This appeared, actually it should be 23, sorry. It appeared beginning of the year. And more recently, in Professor Rajesh Ganpati's lab in Nilendu, they have a very, very unique system to vary the effective temperature. No bacteria, nothing. What you do, in addition to the laser, which is trapping this colloidal particle, you have another laser which fluctuates randomly around this axis. So this creates noise, and what we have shown is it can give you effective temperature as high as 2000 Kelvin, but the water temperature with a thermometer is still 300 Kelvin. So there are many ways to manipulate reservoir. So we call it reservoir engineering. We did reservoir engineering using bacteria. We are doing reservoir engineering using coupled particles, and this one reservoir engineering using photons. So we call it photon phantom. So there is a photon phantom which you can play with and get any statistical property of the reservoir. And so today I'll only talk on this work, which is under final round. And more recently, the reservoir now has been replaced. Instead of water, we have replaced with a viscoelastic gel. This is our old love, you know, the surface. Love never dies. So you have to keep on nurturing it. So here what we show is, even at small time, the power and the efficiency and the work doesn't go down, because the elasticity of the gel helps to restore reversibility, which is what I will not talk. It's in the final round. So I will only give you the key results of this, so that I'll tell you why we are excited. This is the paradigm which has not been broken for the last 250 years. It is a paradigm that you have to sacrifice efficiency to get the maximum power. This happens because in quasi-static limit, why do you get this? Because if the cycle time is much, much more than any relaxation time, because there is a finite time when the engine and the reservoir will exchange heat, right? Because due to thermal conductivity in macroscopic system. As long as this is satisfied, you will have the quasi-static limit. In the last bacterial experiment, our cycle time was 22 seconds. Theoretically, it has been shown very recently in the last 4 or 5 years, you can violate this trade-off with very exotic constructs. I can't tell you how exotic they are because none of them can be implemented in experiments. So there is a beautiful theory framework where they bring out the key point. I'll just give you the key point because that's the heart of these theoretical attempts, almost 10 of them. If you can manipulate engine, which is the what you said, your particle trap, and the reservoir, if you can bring their interaction under control, they should not be independent of each other. If you can couple them, theoretically it has been shown you can look at the breakdown of this trade-off. But nobody knows how do we do this experimentally. So what we thought is what I'll tell you. I will not come to this. What we will do is, what we did, now we don't vary the temperature of the water the way by heating and cooling. You put a electrode around the trap where you apply white noise voltage. Voltage is applied, it's a electrophoretic mechanism, and it is applied randomly. It's a white noise. So it's a 2 kilohertz voltage varying plus 0.5 volt to minus 0.5 volt. And if you solve the Langevin equation, which is done in this 2016 heat engine paper on the Brownian Carnot engine, the T effective gets enhanced, not the normal temperature of the bath, but also something which depends on the strength of the noise. This is the electrophoretic noise. This is the noise on the capacitor. Now you have a way to control the effective temperature of this. So this is the experiment we do. You have put 2 copper electrodes very close, and this is where the colloidal particles are trapped in a tweezer. Do the protocol. I will not go into detail, but the beauty is why it is so brings the interaction. The reason is when you do this electrical voltage, you get the ions which are surround the colloidal particle. So you have an ion cloud which you have to take care. That relaxation has a time scale which is of the order of 4 to 5 milliseconds. And that time scale is now very important in this whole business. So without giving you all the reasoning for it, which you can control, we showed that for a given voltage, fixed voltage, the temperature you will get will not be independent. This is independent if it is a very stiff trap. But if the trap is soft, then the effective temperature depends on the K. This is exactly the system bath interaction. K is your decide the Hamiltonian of the system, that is the engine, and T effective is your bath. So here you have a coupling because of electrophoretic noise. Let me give you the detail last. So this is the final result without worrying about the. You look at the work done. With tau cycle very large, 50 seconds, you have what you call theoretical limit of the Stirling engine. And as you come down, it is coming down. This is the theoretical expectation. But now, moment you cross this 100 millisecond, instead of becoming negative, zero, it's crossing this, it starts going up. You can see the number of data points. And you have a finite work when the engine is moving very, very fast. And we could go up to 10 milliseconds of the cycle time. Efficiency, if you plot, which is the work done divided by the heat input, Q hot, you can see this is what is the normal expectation, decrease. But now here, actually, because the tau is becoming small, it exceeds even the Carnot limit, or it reaches the not exceed, reaches the Carnot limit. So here you have a situation at small cycle time, which is what you will like ideally. You want to have fast engine. Instead of becoming stalled, instead of not working, it is giving you a large efficiency and finite work done. And if you plot efficiency and power on the same thing, it's completely violated. So this is the one where the violation is not there up to this as expected. But this regime is totally, totally new. So we have now very large power at small tau. That is fine. Also, we have large efficiency. So this trade-off is broken. How did we break it? Let me remind. How does the Stirling cycle look? In T and K is like volume. This is the beautiful Stirling cycle for 550 seconds. No surprise. But when you start playing with the tau cycle small, it is highly distorted. And this can explain all this. And we can show that this is totally broken. So the moral of the story is, theoretically, it was predicted that bath and system, you cannot have independent one. Can you, if you can bring coupling, which is a billion-dollar question for macroscopic heat engine. We do not know how it will happen. But in mesoscopic heat engines, you can do that. And what we have shown is maximum efficiency can be reached in finite time for irreversible engines by tailoring engine bath interaction. And this can be broken for microscopic system. So that's why we feel very excited that this whole paradigm, which is there for last 250 years, can be broken for this nano heat engines and experimentally demonstrated. Now, okay, 10 minutes, right? I will now tell you the second part of my title of my talk. And I moved to Delhi on 25th April in office of PSA. And this is where the Vigyan Bhawan comes, because PSA office is in Vigyan Bhawan, Annex. And as you know, Dr. Chidambaram was the second PSA for 16 years. First PSA was Dr. Abdul Kalam. And the third PSA was Dr. Professor Vijay, again, TIFR connection, DAE connection. And 25th April, I took over in Vigyan Bhavan Annex. And this is the Vigyan Bhavan Annex, and our office is somewhere there. And so again, this art, which I said AI tool, just to amuse you, this is what it tells you, that if what is the image of this generative AI, which it will generate, just to amuse you. Now, I'll just take few minutes to introduce you to what this office does or expected to do. So the aim of this office is to provide pragmatic and objective advice to the Prime Minister and Cabinet on matters related to science, technology, and innovation. This is the broad mandate. And if you look at more carefully, it covers all aspects. It enabling future preparedness in emerging domains of science and technology, fostering effective public-private linkages, which is again very critical, as we'll discuss later, for driving research and innovation, and S&T fundamentals with applied research in collaboration with multi-stakeholders, both in central and state, and driving innovation and technology delivery towards solving socio-economic challenges for sustainable growth, providing an enabling ecosystem for technology-led innovations, and formulating and coordinating major interministerial S&T mission. So we do not come under any science ministry. We are ministry agnostic, and that's why we can work with all the departments, be it civil aviation, be it MNRE, be it DOT, MIT, and of course the science department. So it spans across all the S&T sectors. We have two arms in this, and this is one is called the Prime Minister's Science, Technology, Innovation Advisory Council, which has 6 members. This is to develop a futuristic roadmap for science and technology and advise the Prime Minister. And the second one, equally important, is called Empowered Technology Group. And this is to oversee national level policies related to procurement and induction, facilitate R&D and timely advice and all that for technology development programs. For example, the drone policy, how can be done, what has to be done, and so on. So this comes under Empowered Technology Group. So the idea here is that you need interdependencies of fundamental science, you need innovations including business models and enabling technology to do all these technologies which country needs. And that is the whole paradigm of taking country forward in a technologically competitive manner. Now, there are many, many technologies. One cannot really just say one or two. This is just a snapshot of something which you come across in daily life. We have immediately the quantum frontiers to handle. We have advanced communication technologies like 6G. We have digital transformation in which India has done extremely well, probably the best in the world, and artificial intelligence. Clean energy is something which we cannot ignore. And One Health mission is what we started last year to learning from the COVID experience. So what do we have? In PM's type, in the last 4 years, what we have is many missions which have been launched. So we have Deep Ocean mission launched, Ministry of Earth Science leads it. So Office of PSA does not lead any mission. We do not implement any mission. We are more in the advisory role before the mission is launched, working out all the domains and also make sure that it runs when it is launched. So we have that role, National Natural Language Mission, Artificial Intelligence by Mighty, Waste to Wealth, which is run by our office, Accelerating Growth of New India Innovation, Agni, by our office. Again, Mobility Mission, under that the Green Hydrogen Mission has been launched by MNRE. And more recently, Quantum Mission was launched, as you know, very recently by the country, which is led by DST with another 6 departments joining. And very recently, we are working to launch One Health Mission, which will be steered with about 11 ministries, but the lead ministry will be ICMR. And another mission which is in the making, or we have to work on it, is called National Livelihood Mission, where the S&T outcomes can be really taken to masses in less privileged societies, in villages and so on, how it can be done. So this is a broad theme. And more recently, for example, to give you an idea, on July 25th, we had the Technology Advisory Group meeting, and we looked at alternate battery technologies, which countries should focus on, carbon capture, utilization and storage, what are our strengths and what are our weaknesses. And artificial intelligence is a huge thing, and a task force is being created as we speak to really take it fast forward with responsibility. Because generative AI, as you know, has other side of it. So you have to now integrate and balance the usefulness as well as the risks of this. So I don't think I have too much time, but what I'll do is I'll just give you 1 or 2 examples of One Health Mission, for example, which is we all know that human health, animal husbandry and wildlife, they are all interconnected. And diseases are going across the 3 sectors, and we cannot take them separately. So One Health Mission is really to look at the future pandemic preparedness by involving almost 11 ministries and state governments. So here the idea is all the ministries are doing something or the other in One Health, but there are lots of technology gaps. So this mission will look to plug those technology gaps and make us future ready for the future pandemics. So there are lots of players. I will not read it. There are 2 levels of high-powered committees, various private sectors, NGOs, academic institutes, international partners are there. And this is what is now going to the cabinet sometime soon. A lot of technology needs we have identified in the mission, what you need for surveillance, what you need for vaccines, what you need for data, disease modeling, and so on. So this is a some picture which is evolving. And the most recent mission is the Quantum Mission, and TIFR is doing extraordinarily well as a leader in quantum domain. I had this another meeting 2 hours back with the players here. There is no question that you need quantum technologies. It has 4 aspects: quantum computing, quantum communication, quantum sensing, and quantum materials and devices feeding into all these 3. They are not all 4 independent, they are interdependent. And the mission which is launched and will be managed by DST will look at all 4 verticals. So this is something which is evolving. It has been announced, but now all the committees and all that and the structure is being made. I will not spend time. This is something worldwide it is happening. We have started it, and it will take us a lot of effort in a short time to really see that we don't lag behind this, and we have to have quantum safe world. It is a reality. It's not a question whether we should do it. It is a question, how do we do it soon? That's the question we have to ask. And luckily, the Nobel Prize in 2020 is again on quantum technologies. I will not give all the quantum, there's 101 on quantum mechanics and why quantum, the second revolution in quantum mechanics is happening. But what I want to show that this settles the debate once for all, this artificial divide between basic science and usefulness. So this famous plot, which you would have seen a million times, what it plots is whether it's a fundamental understanding and consideration of use. This sector is called the pure basic research Bohr sector. This is called pure applied research Edison center. And when you have both these high, it's called use inspired basic research, which Dr. Chidambaram also called directed research or whatever names. And this is the posture. So this is what, but what you want to remember is that in this plot, time is not there. What you have to remember is the beginning can be the basic science, but then it will become the most useful thing. And quantum technology is a case in point. Other case in point, of course, is GPS, which depends on general theory of relativity, cryptology, and so on. I don't have to tell this audience, you are more familiar than me. I will not give all this talk on green hydrogen, which is a mission. I will say that enormous work has been done in the last 6 months, and we have come out with a R&D roadmap. And this is there as we speak on MNRE website, inviting comments from scientists and all the stakeholders if we have missed out. And very soon, this will be R&D roadmap will be implemented in the country. This is where we have played a big role. And last initiative is what we do. So I'll take only one mission, one platform called Manthan platform, which is launched. So what we have done, so Project Manthan was launched on 15th August last year, 2022. It's less than a year. It's about 11 months. In 11, the idea is that you have people who demand solutions. They say we must have the solution in the country. What scientists are doing? What are you doing? What is the mechanism if industry wants to ask a question, NGOs want to ask, embassies want to ask, philanthropists want to solve a problem like foundations, public sectors, MSMEs, and so on. These people have the problem statement or their intention to really get the solution. Now they will go to various supply side, which is R&D, our academic institutes, our startups, various people, academic sector, national labs. They will say that, look, we can work for you in a way which is mutually beneficial. So we have demand and supply side on this platform. It's a very, very transparent and democratized platform. And we have large number of opportunity providers who are willing to fund R&D, even basic as well as applied on given problem statements. So we have 254 opportunity providers, which means funders on this platform, and 175 industries have been engaged. lot of central ministries have been engaged. And in the last 11 months, 2690 crores have been finalized with these things. Most of them are finalized, some are in the final stages. And total number of central ministries, which are the opportunities, are 25. So central ministries like Ministry of Jal Shakti, MIghty, they have put problem statement on this platform. So I urge you to go to that platform and see if you would like to contribute to the national priorities as well as otherwise. So a large number of STI clusters, which also comes under our office, 6 of them have been done. I will not, these are some examples where the funding as high as 68 crores have been given to Center of Excellence on this energy. So it's a very, very wonderful platform where we can do this matchmaking and see how really we can use our ecosystem to really solve the problems. And this is the attempt by Office of PSA. I will not give you on the clusters. And last one, which you might be curious, is the NRF, which is another big opportunity where again Office of PSA has played a role. And again, here we need to bring collaborations between institutes, institute and industry, institute and national labs, universities, and we need to go to tier 2 and tier 3 academic institutes. We have to have partnerships, which we have written in the bill. We have professorships, which can be taken in the smaller universities and so on funding. So this is something evolving. So let me close this. Why do we collaborate and do science without borders, which means you really don't have to think of physics, chemistry, biology. We have complex problems which may not be for single discipline, and discoveries usually happen on the borderline, and we need to collaborate with each other for this. So thank you once again. I'm sorry if I took more time, but this is something I thought.
Thank you, Professor.
We can have 15 minutes.
Thank you, Professor, for such a engrossing, wonderful talk. And now talk is open for questions and comments. Due to this time constraint, we can only take 1 or 2 maximum questions. Yes, Sandeep? Yes. Can you provide?
Hello, Dr. Sood. So this Manthan seems like a great idea of kind of people listing down their problems and then scientists with their skills trying to match the two. Any successes you can report? How is it working out so far? Anything else
So
you can do?
already some projects in 11 months, it's not too long, have been closed with some deliverables, but many of them are halfway. So already 2,600 crores have been committed. Lot of it has been released, and the outcomes will start coming in next few months. But some of them which are already almost close to that, we do not control that. We will not be able to control that. We are not policing a project. No, that is outside our expertise and outside our even the bandwidth of our office. So we will not have that. It's a very, very wonderful team strategic alliance division. You can go to the PSA website and you can see what are the open challenges at a given time. Every few days or month, I guess, or few weeks, new challenges are posted by the people who are giving the opportunities, and they cover R&D, they cover the missions, everything, Center of Excellence, everything.
Gobindo? Gobindo.
The mic is with me. I'll take the question. Professor Sood, I have a question about out here in the middle, straight ahead. I had a question about your work on these non-equilibrium baths. In some of the examples, you showed that you are actually creating this non-equilibrium bath by applying these voltages or these fluctuating lasers. Does one have to worry about the energy requirements of creating those non-equilibrium baths and to be factored into the
No,
overall
we don't factor
efficiency?
that.
Okay,
The factoring is what is the work output of the engine and how much heat is transferred through this fluctuation to the engine.
okay,
How the reservoir is engineered, that is not even in the definition of Carnot and Stirling cycle.
I see.
It's not there.
Okay,
So that's the way thermodynamics is defined.
okay. All right, thanks.
Gobindo, last question.
Yeah, so this is not what you talked in this here, but this is come from your office, that Mega Science Vision 35. How seriously we can consider that?
How serious I can?
We can consider that what went from the, let's say, example, the Mega Science Vision 35 from your office. So some many feedback was taken from us
Yes,
and we have given some feedback.
correct.
And
So
how,
I think somebody asked me this at lunchtime. I don't know who asked me. Yes, so the first on the nuclear physics, it has been submitted and I gave the response that we need to find somebody who can handhold this. That's the brief. As I mentioned repeatedly, Office of PSA does not run any mission. No, we facilitate that and make sure that whatever we can do, that there is a taker who is convinced that we have done all the homework and take it forward.
no, my question is that how much you can influence the minister that if something was
Not a public
promised-
question, sorry. No, sorry.
No,
Not a
I
public
was saying
question.
particularly-
No, I don't know the answer. Thank you.
Then I can-
Okay.
Yeah.
Okay, so I think because of we are already pressed for time, we will stop this question and answer. He will be available during the tea time. So let me thank Professor Padma Shri, Professor Sood for coming here all the way and giving such a wonderful and engrossing talk. Engaging us all. Now, just as a formality, I have to thank all the people. So it's my pleasure and privilege to thank all the people who made this possible. So we wish to express our gratitude to the director, TIFR, and the entire administration of TIFR for their enthusiastic support. We thank the speaker, respected Padma Shri Professor Ajay Sood, FRS, for his wonderful lecture covering several decades of his adventure in Vigyan. And it must have been a Herculean task to summarize it in such a short time. And so we wish to thank Mr. Kishore Menon, Ms. Snehal Sawan, Central Services, Auditorium, Gardening, Canteens, Transport Security, PRO Office, and the Registrar's Office. So we hope to see you again next year, and take care and have a nice and wonderful evening. Thank you very much.